Hello, everybody. Welcome back to another business calculus video. Here, we're going to be talking about the area between curves. So, what is the area between curves? Well, we've used the definite integral as our tool for finding the area under a single curve, or rather, the signed area under a curve, right? If I was to draw a curve like this and find this area with a definite integral, it would output a negative number. Right? Because the definite integral is measuring positive and negative as well as area. But what if I wanted to just find that area without the negative sign in front? Or furthermore, what if I more generally wanted to find an area of a curve, the area of a region that is bounded by more than one curve? So for instance, maybe I have a situation that looks like, I don't know, this, where I have some function f of x, another function g of x, and between a and b, I'm trying to find the area of this region right here. Well, how can we go about doing that? Well, let's notice something. This area right here is the entire area under f of x minus just the red area under g of x. So if we put the f of x in blue, hopefully that picture isn't too overdrawn, but we notice that the white area that we want is the area under f of x minus the area under g of x. But we know how to formulate that in terms of integrals. This is the definite integral from a to b of f of x dx minus the integral from a to b of g of x dx. And for the sake of giving it just one nice compact formula, we can use the sum rule to merge those two back together and get that this is the integral from a to b of f of x minus g of x dx. Alright, so let's state this formally with a theorem. Let f and g be integrable functions. Your book says continuous, but I'm pretty sure it holds for any integrable functions. Let f and g be integrable functions such that f of x is greater than or equal to g of x on a to b. So we'll notice here that our function f of x was completely above g of x, and that's why this whole thing is working together. Then, if you have this situation happen where something like this is the case, the area of the region bounded by f of x, bounded above by and bounded below by g of x on a to b. So the area in our given interval that's bounded above by f of x and below by g of x is given by the integral from a to b of f of x minus g of x dx. x. So exactly the situation we observed with our picture over here, just noticing that the condition that made all of that work was that f of x was greater than or equal to g of x the whole way through. There wasn't any kind of crisscrossing going on. We will handle that case in a bit though. Oh, and a quick cool side note about this theorem. I know in that first picture I drew, it had both f and g as positive functions. This actually holds no matter whether f and g are completely positive, completely negative, or some mixture of the two. In just the negative case, let's draw that a little higher. If you have just two negative functions, f of x and g of x, and you were trying to find, say, this area here, the integral of f of x would measure negative this, and then integral of g of x would measure negative this whole thing. So if you subtract that, if you subtract the whole thing from that, you'd end up with positive this. So it all works out. Basically, you can work with this no matter whether your functions cross the x-axis or not. It's a very good theorem. All right. Well, let's do a few examples. Oftentimes, your book will give all of the information about bounding in equation form, not just saying, oh, it's f of x, here's f of x, here's g of x, and here's your interval. They'll say bounded by these equations, which it's the same thing, but just to give you an example of the vocabulary that might get used. They might say something like, find the area of the region bounded by g of x equal to negative x cubed plus 4x minus 4, and the lines x equals 0 and x is equal to 2. They might say like y is equal to negative x cubed plus 4x minus 4 instead of g of x. Same thing. Alright, so one of the most helpful things you can do with a problem like this, if you're having a hard time figuring out what's going on, is draw a picture. It doesn't have to be a great picture. A rough sketch will go and do wonders in this case. So if you were to sketch g of x, we know we're trying to go between the lines x equals 0 and x equals 2. So that's really all I care about, is that region. I don't care about what's going on outside of there because I'm bounding by those two lines. Okay? And if we sketched g of x in that region, it would look kind of like that. And you could get that in multiple ways. You could put some test points in there, everything like that. Just plot the function roughly in that region. So we're looking for the area of the region bounded by that function and the lines. I guess you should also say, and the x-axis. Oh, yeah, that was on my notes, I just didn't write it. So, it's bounded by these things, right? And we're bounded by g of x and the x-axis. That means we're trying to go for this interior region right there. Alright, so what's our answer? Well, let's notice, the x-axis is always above g of x on this region between 0 and 2. And the x-axis corresponds to the function f of x is equal to 0, right? It's the function that's just completely flat at 0. That's the x-axis. So now, by this theorem, our area, if we call it A, then our area A is equal to the integral from A to B of 0 minus g of x. dx. Or in other words, if we just plug the definition for g of x in there, 0 minus negative x cubed plus 4x minus 4 dx. And we're integrating not from a to b, but from 0 to 2. Between 0 and 2, bound above by the x-axis, 0, and bound below by this g of x function here. Alright, let's evaluate that integral. This is equal to the integral from 0 to 2 of x cubed minus 4x plus 4 dx, which is the integral from 0 to 2 of x cubed dx minus 4 times the integral from 0 to 2 of x dx plus the integral from 0 to 2 of 4 dx, applying the sum rule and the scalar multiple rule. Alright, where do we go from here? Well, we just keep evaluating these definite integrals. Applying the fundamental theorem of calculus, since we just have things we can straight up integrate, we don't have to worry about any u-subs changing, any boundaries or anything like that. We can just straight up integrate these. And this becomes x to the 4th over 4 divided from 0 to 2 minus 4 times x squared over 2 going from 0 to 2 plus 4x as x goes from 0 to 2, which is 2 to the 4th over 4 minus 0 to the 4th over 4 minus 4 times 1/2 is 2. So we're going to have 2 times 2 squared minus 2 times 0 squared plus 4 times 2 minus 4 times 0, which is equal to what? Well, that's 16 divided by 4. Yes, 16 divided by 4. So we're going to have 4, that's 0, minus 4, because again, that's 0, plus 8. Look at that. It's just 8. That's the area under that curve. Well, not under that curve, bounded by that curve. And you'll notice it's just the same as the negative of the normal definite integral here, and that's because we're working with just a single curve and the x-axis. So this is kind of the simplest case for a negative function, but we can do better. Or rather, perhaps not better, but more complicated. I'll leave that for you to decide whether you think that's better or not. But it's certainly more helpful in terms of real-world problems. Alrighty. For example, let's find the area of the region bounded by f of x equals 3x minus 2, g of x equal to x squared minus 2, and the lines x is equal to 1 and x equals 2.5. Alright, so if we sketched out a picture of this, again, you could get this picture however you wanted. On test or something, I'd provide the picture so you wouldn't have to find it. But if you drew this picture, you would get a region that looks kind of like this. And this is f of x here, this is g of x right here. This would start curving back up, start going back down. And let's see here. 1 is roughly here, and 2.5 is like here-ish. So we're really looking for a region that looks kind of like this. That's very much not to scale, so let me scale that a little bit better for us. There we go. Alright, still not the greatest sketch, but slightly better. So we have a region that is crossing the x-axis, but that's no problem. Our theorem still takes care of it in a single step. The only thing we have to do is decide, okay, why did I erase this? I don't know. The only thing we have to do is decide, okay, which parts of the function are above the other. And we see that between 1 and 2.5, f of x is above g of x. So, by our theorem, our answer is the integral from 1 to 2.5, since that's the side boundaries for our region. The integral from 1 to 2.5 of 3x minus 2 minus x squared minus 2 dx. F of x minus g of x, because f of x is above g of x. This is the integral from 1 to 2.5 of, okay, we have negative x squared plus 3x, and then we have a minus 2 plus 2 right there, so those cancel out, and we just have this. Alright? And that's equal to negative integral from 1 to 2.5 of x squared dx plus 3 times the integral from 1 to 2.5 of x dx. Which is equal to negative x cubed over 3 as x goes from 1 to 2.5 plus 3 times x squared over 2 as x runs from 1 to 2.5. Alright? Get out your calculator or whatever other device you care to compute these numbers, most specifically 2.5 cubed. 2.5 squared I can do off the top of my head, but not 2.5 cubed. So we'd have negative 2.5 cubed over 3 minus negative 1 cubed over 3 plus, here we have 3 halves. So we have 3 times 2.5 squared over 2 minus 3 times 1 squared over 2. That's just the setup from the notation. 2.5 cubed ends up being 15.625. We're going to have plus 1/3. Plus, okay, 2.5 squared is 6.25. Times 3 is 18.75. And then 1 squared is just 1, so we can have minus 3 halves. So we're going to have negative 14.625 over 3, because we have that negative there, plus 15.75 divided by 2. All right, and if you put all that through a calculator, 0.625 divided by 3, plus 15.75 divided by 2. Oh! Well, that's nice. I made those numbers up off the top of my head. I have no idea how that turned out that nice. Lucky day. Okay. So, we have 3 as our final answer. But really, the number isn't the important thing. The important thing was the setup. Realizing, hey, in our region, the region is 1 to 2.5, and we have f of x greater than or equal to g of x, so this is our setup. Quick question, what happens if I said I wanted to change the region if I changed the sideways things? What if I just took away and the lines, and I said it's just bounded by these things? So, new example using the same functions. But we're going to say instead of just bounded by those functions and those lines, what if I just say bounded by those functions? What does that mean? Well, sometimes if you choose the functions correctly, they'll determine a natural region of their own. For instance, there's a very clear and natural region bounded by these two curves, which is namely this entire thing, and it'd be helpful to find this area. So, we need to do two things. We need to set up our integral, and we need to find out the boundaries of that integral. So we're still going to have, this is still f of x and this is still g of x. We still have f of x greater than or equal to g of x on our region. We don't know what our region is yet, but we know that it is greater than or equal to g of x on the whole thing. But what should our region be? Basically, I'm trying to figure out what should our bounds of integration actually be? Well, it's going to be at these two intersection points of the function. That's our bounds, right? We're going to go from here up to here to here, wherever those two things might be. How do we find those two x-coordinates? Here's the cool part. We can just set the two functions equal to each other, and whatever values for x pop out, those are going to be the intersection points in the function, right? Because that's what it means for a point to be on the graph of both functions. It means it's an x-coordinate that makes those two things equal to each other. All right, so we solve f of x equal g of x to find bounds of integration. Alright, so f of x is equal to g of x means that 3x minus 2 is equal to x squared minus 2. Moving everything over to one side, you get 0 is equal to x squared minus 3x. So in other words, x times x minus 3. Which means that x is equal to 0 or x minus 3 equals 0, aka x is equal to 3. So we have our two intersection x-coordinates, 0 and 3. Now we can set up our problem. Our problem is now the integral from 0 to 3 of 3x plus 2, or minus 2, excuse me, minus x squared minus 2 dx. Because f of x is greater than or equal to g of x on the entire region. So we have f of x minus g of x. And our boundary should be 0 to 3 because those are the 2 points. So it turns out that, hey, that was 3 all along, and that was at 0. Cool. So let's actually compute that integral. Very similar to the last one, just with change bounds. So I'll kind of speed through it. It's going to be the integral from 0 to 3 of negative x squared plus 3x dx, which is negative integral from 0 to 3 of x cubed dx plus 3 times the integral from 0 to 3 of x dx, which is, oh sorry, this is squared right here, which is negative x cubed over 3 going from 0 to 3 plus 3 times x squared over 2 as x goes from 0 to 3, which is negative 27 thirds minus 0 thirds minus negative 0 thirds, sorry, plus 3 times 3 squared is also 27, so you'd have 27 halves minus 0 halves. Just running through the evaluation very quickly. And this is negative 27 thirds plus 27 halves, which ends up being 27 over 6. Yeah. Right, because you have 1/2 minus 1/3, which is 3/6. Yep. Cool. 27/6. So, at this point, we've kind of gotten a grasp of functions that just lay one completely on top of the other. Sometimes we're given boundaries to boundary equations so we can figure out our region. Other times, if the region is naturally determined by two functions, we find the bounds of integration by setting the functions equal to each other. I mentioned earlier that our theorem only holds if one function is completely above the other. But what about functions that crisscross? So for example, what if I wanted to find the area of the region bounded by f of x equal to x cubed minus 11x squared plus 38x minus 37 and y equals 3. I know that's a complicated function. It took me a little bit to wrangle it all together, but there's a reason for it. If you were to graph these functions, they would look like, roughly, this thing. So we have 3, and here is f of x. So, we're trying to find the area of the region bounded by those two things. That's going to be this thing here. This is what we want. So how can I find this region? Well, to determine my boundaries of the integral, I need to find some intersection points, so we know that's going to have to happen. But how do I deal with this crisscross? Our function only works if f of x is greater than or equal to g of x the whole way through. And that's not the case here, right? Here, f of x goes both above and below our secondary function, which would be g of x equal to 3. So how do we deal with that? The answer is we use that splitter property of definite integrals and we say, hey, this entire area is just this area plus this area. We're cool with that. So what if I just split it right down the middle there? And if we do that, then we say, oh, then on each of those individual subregions, there is one function that's clearly above the other. F of x is definitely above 3. this whole place, and 3 is definitely above f of x on this whole region. So if we split it up like that, we can solve our problem. So the question is, okay, what should my bounds of integration be for each of them? Right? If we call this A, B, and C, what should A, B, and C be? Well, we're going to use the same technique as the previous problem. We're going to set these two things equal to each other, and we're going to solve for 0. Or not for 0. We're going to solve when they're equal to each other. So we solve x cubed minus 11x squared plus 38x minus 37 equal to 3. In other words, x cubed minus 11x squared plus 38x minus 40 is equal to 0. Alright, so most of the time you'll be given functions where this equation is a little bit easier to solve. But on the off chance you're not, you could use, say, the rational roots theorem, if you remember that from a pre-calculus course. The rational roots theorem would be your primary way to go to try to factor this polynomial here, since that's what we would need to do to find the zeros. I will just straight up say that these zeros are at 2, 3, and 5. Or, sorry, 2, 4, and 5. So this actually becomes x minus 2 times x minus 4 times x minus 5 is equal to 0. After some work. Which I will not be requiring you to remember how to factor high degree polynomials that don't factor easily. If I gave you something like this, you should probably be able to factor that just fine, right? Because that becomes x squared times x squared minus 1. You should be able to factor something like that. But in general, I'm not going to give you guys super complicated things and be like, factor this. I'll just give it to you in factored form. So for instance, I might have given you, say, f of x is equal to x minus 2 times x minus 4 times x minus 5 plus 3. And that would have worked. Okay, enough of a side tangent. The long answer is by hook or by crook, you get that x minus 2 times x minus 4 times x minus 5 is equal to 0, which means that x equals 2, 4, or 5. So we know that these are the coordinates of our things. 2, 4, and 5. So how do we set up our problem? Once we get all this information, all this getting of information is preliminary work. How do we set up the integral to get the actual area? Well, we need this area first. What's this area? Well, by our theorem, since f of x is greater than or equal to 3 on this region, we say that that area is the integral from 2 to 4 of f of x minus 3. dx. Now we need the area of this region. What's the area of this region? Well, by the very same theorem, this is the integral from 4 to 5 of 3 minus f of x dx. And now we can evaluate our integrals. So the temptation here is to try to merge those two integrals together. The sad truth is you can't. They have different bounds of integration. So indefinite integrals can always be merged, but definite integrals have to have the same boundaries of integration for things to work out. So we handle each of these things separately. They don't just cancel out and become one giant zero. Okay, well, let's start evaluating. this would be the integral from 2 to 4 of f of x minus 3, so this whole thing minus 3, is x cubed minus 11 x squared plus 38x minus 40 dx plus the integral from 4 to 5 of, okay, 3 minus this whole thing right here would give us negative x cubed plus 11x squared minus 38x plus 40 dx. Alright. Make sure you have this picture down. I'm going to erase it. Well, now we can just evaluate our integrals. So this gives us x to the fourth. Oh, well, I suppose I should do my due diligence. Actually, no, exercise. When you do this, you should end up with x to the fourth over 4 from 2 to 4 minus 11 times x cubed over 3 from 2 to 4 plus 38 times x squared over 2 from 2 to 4 minus 40x going from 2 to 4 plus, well, I guess plus minus, right? Because we have a minus in here. So we're going to have minus x to the fourth over 4 going from 4 to 5 plus 11 times x cubed over 3 going from 4 to 5 minus 38 times x squared over 2 going from 4 to 5 plus 40x going from 4 to 5. Alright, and if you go through all of the work to evaluate that, I'm going to do that off screen since that's just a lot of ugly computation, but you should try it yourself, and if you do, you'll get, okay, you should get roughly 37 over 12. Once you do that whole big thing. How about that? So just over 3, it actually turns out. Let's do another example. One that'll hopefully be a little bit easier in terms of finding those intersection points. So, for example, let's find the area of the region bounded by f of x equals 7x cubed minus 6x plus 4 and g of x equal to x plus 4. Alright, so if you were to sketch this region, it would end up looking roughly like this, if you were to try to sketch those. There we go. Alright, so we're looking for, and it doesn't dip down quite that far. Bad sketch. There we go. So we're looking for this region right there. as I said, if I ask a question like this on a test, I will give you guys the picture of the function, so you don't have to worry about trying to draw them. Because goodness knows, that would be annoying. And everybody has graphing calculators, so I just don't want people using them. Okay. How would we set this up? Well, this is our g of x right here, the straight line, and our f of x is the curvy one. So we see we have a very similar setup to last time. F of x is above g of x for a while, and then below g of x for a while. We should figure out where those intersection points are at. So we solve 7x cubed minus 6x plus 4 is equal to x plus 4. Okay, subtract everything on one side, and you get 7x cubed minus 7x is equal to 0. That's something we can handle factoring. That's 7x times x squared minus 1 equals 0. So either 7x equals 0, or x squared minus 1 equals 0, x equals 0, or so you do the algebra and you turn out that either x is 0 or it's plus or minus 1. So these coordinates were actually -1, 0, and 1 all along. My sketch is just, not the greatest. But now we can set up our integral. Our area, our final answer, is going to be the integral from, between -1 and 0. Right, so our entire area spans -1 to 1, but we have this split at 0. Between -1 and 0, f of x is greater than or equal to g of x. And it's below g of x on 0 to 1. Okay, so with that setup out of the way, from -1 to 0, we have f of x minus g of x. So we're going to have 7x cubed minus 6x plus 4 minus x plus 4. We have that plus the integral from, how about the second region? Well, in that second region, f of x is less than or equal to g of x, so we have the integral from 0. Oh, that's interesting. Sorry, give me a second. All right, never mind, something popped up. All right, so we have the integral from 0 to 1 of g of x minus f of x. So we have x plus 4 minus 7x cubed minus 6x plus 4 dx. All right, again, I'm going to erase this side, so make sure that you have it all down. Also, please note, it is important that you do the splits, because if you don't split it like this, if you just try to do one of them, you would end up with 0, because the areas would actually cancel each other out, and that would be bad, because that's not the integral we want. Okay. Let's evaluate. This is the integral from -1 to 0 of 7x cubed minus 7x dx, plus the integral from 0 to 1 of -7x cubed plus 7x dx. So you can see the split is very important. Let's evaluate those integrals. This is equal to 7 times x to the 4th over 4 as x runs from -1 to 0, minus 7 times x squared over 2 as x runs from -1 to 0, minus 7 x to the 4th over 4 as it goes from 0 to 1, plus 7 times x squared over 2. from 0 to 1. Now, I know in both the last example and this one, there was kind of this symmetry here, where this one was just the negative of the previous one with the boundaries flopped. That's not always the case. It happens to be this way because we're using symmetric functions that have this kind of symmetry, but it's not true in general, so just keep track of it. Don't just do one half and be like, oh, the second half is automatic. It's not, just keep track of them separately. This always works. Okay, let's evaluate those integrals. This is 7 times 0 to the 4th over 4 minus 7 times negative 1 to the 4th over 4 minus 7 times 0 squared over 2 minus 7 times negative 1 squared over 2 minus 7 times 1 to the 4th over 4 minus 7 times 0 to the 4th over 4 plus 7 times 1 squared over 2 minus 7 times 0 squared over 2. Alright, you evaluate all of those things out. Negative 1 to the 4th is positive 1, so you have negative 7 fourths. That's 0. Minus, 0 minus negative 1 squared is 1, so we have minus 7 halves. Minus negative 7 halves is plus 7 halves. Okay, we're going to get another minus 7 fourths from there, from that third term. And then from this fourth term, we're going to get another plus 7 halves. And that ends up just being 7 halves. All right, so the most important thing, as I said, is setting up this problem properly. Solving the intersection points, because we were not given explicit boundaries. We solve for them. Then we set up our problem by deducing, okay, which one is above which for our given regions. And then once we set up, now we can just evaluate the integrals and it all works out properly. Let's do another problem. We'll do 2 more examples and then we'll call it good. Alright, find the area of the region bounded by f of x equal to x e to the negative x squared, y equals 0, x equals negative 1, and x equals 1. So here we're given our 2 regions. Let's just sketch what we've been told to. It'll turn out, if you were to draw this, it would look something like that. And the negative 1 and 1 thing would be roughly like here-ish. So we're looking for that region roughly right there. So again, very important not to just take a definite integral of the entire thing. Those 2 areas would cancel out and you'd get 0, which would be bad. Because it's very clearly not 0 area. So how do we set this up? Well, okay, we need to figure out where that intersection point is. Hopefully it's pretty obvious that it's at 0, but let's say it wasn't. Then we solve x e to the negative x squared equals 0. X is equal to 0, or e to the negative x squared equals 0. E to anything is not 0. If you tried to take the natural log on both sides, you'd be trying to take the natural log of 0, which is undefined. So this never happens. Which means our intersection point is at x equals 0. we go from here? Well, we're going to set up our integral. We notice f of x is greater than or equal to 0 on this second region right here, on 0 to 1, and it's less than or equal to 0 on negative 1 to 0. So between here, f of x is below 0. Here, f of x is greater than or equal to 0. Which means our area integrals get set up as an integral from negative 1 to 0 of, okay, here f of x is below 0 as we go from negative 1 to 0. So you're going to have 0 minus x e to the negative x squared dx plus the integral from, I'll move that a little lower. Such a beautiful integral sign too. Integral from 0 to 1 of x e to the negative x squared minus 0. Yes, since between 0 and 1, f of x, x e to the negative x squared, is greater than or equal to 0. Alright, let's evaluate those integrals. This is the integral from negative 1 to 0 of negative x e to the negative x squared dx plus the integral from 0 to 1 of x e to the negative x squared dx. Seems like we're going to need a u sub, since I don't know how to do that integral just by the top of my head. What should our u sub be? Well, typically, if we have e to anything, the anything is a good choice of u sub. So let's try it. If we let u equal negative x squared, then du is negative 2x dx. And we're going to run the same u sub for both of them. We don't have to necessarily, right? You can do each integral separately. Like I could find that one, and I could find that one, and I could do them separately and add them together. That would work. Here, it turns out the same u sub will be useful for both of them, so we'll just take the whole thing. And we see here, okay, this one is only off by a factor of positive 2. Since we need a negative 2x dx, we have a negative x dx. So we need to get 2 in here, and here we need to get a negative to it. So this is equal to the integral from negative 1 to 0 of 1/2 times negative 2x e to the negative x squared dx. The 1/2 times positive 2 gave us the negative 2 here, plus the integral from 0 to 1 of negative 1/2 times negative 2x e to the negative x squared dx. We need to multiply by negative 2 here, so we have a negative 1/2. Alright, now if we run our u sub, let's see what our 3 boundaries are, since we have negative 1, 0, and positive 1, and all 3 of those go through the u sub. Heck, even if you wanted to do it differently, just for the sake of it, let's say it was 2 separate u subs. Let's say b here was negative x squared, and d was negative 2x dx. You don't need to do it with 2 separate ones, but for the sake of notationally keeping track of everything, let's do it here. Okay, what would our new lower bound be? Well, our u sub a here would be negative 1 squared, which is ended up still as negative 1. How about ub? ub would be negative 0 squared, which ends up still being 0. How about over here? Our new upper boundary is now, our new lower boundary is now 0 squared, which is 0, and our new upper boundary would be negative 1 squared, which is negative 1. So here we have a changed boundary point, not on the other one though. So this is the integral from negative 1 to 0 of 1/2 times e to the negative x squared, that's e to the u, and then negative 2x dx is our du. And here we just ran as a v sub instead of a u sub, but same idea. We now have the integral from 0 to -1 of -1/2 e to the v dv. All right? How can we start working with these? Well, we can pull out the scalars, and we can use that rule that says you can flip the boundaries of integration at the cost of the minus sign to get -1 on the bottom and 0 on the top here. So now this is the integral from from -1 to 0, 1/2 times that, e to the u du, minus from 0 to -1, which means plus the integral from -1 to 0. I'll write it out in 2 steps. I have the time. All right, so we can pull out the scalars, and then we can run that. All right, so hopefully you all are cool. All we're doing is saying, hey, we're gonna run 2 separate u subs. We didn't really have to, but we can, right, to help keep track of everything. If you want to run it with just the 1 u sub, by all means, go and do it. Just make sure to keep track of all 3 changing boundary points in your new term. You have to convert the -1 over, the 0 over, and this 1 over. All right, but now that we're here, where can we go? All right, well, hopefully we've learned at this point our name of variable doesn't matter. V could be smiley face or squiggle. The integral, 1/2 times the integral from -1 to 0 of e to the v dv is the same as 1/2 times the integral from -1 to 0 of e to the smiley face d smiley face. As long as you're consistent with your variable choices, it doesn't matter. So if you want, go ahead and just evaluate the definite integrals from here. However, if you're feeling spicy, you could be like, oh, this is 1/2 times the integral from -1 to 0 of e to the u du, plus, I'm just going to change v to a u, right? And if I change all the v's to just a plain u, that works out. Plus 1/2 times the integral from -1 to 0 of e to the u du. And now we have the same integral, which means we can combine them. Same bounds of integration and same variable, so that can be combined, essentially is what I'm saying here. And we have 1/2 plus 1/2, which is just 1. So now it's just the integral from -1 to 0 of e to the u du, which is e to the u going from -1 to 0. That'd be our final answer. And if you wanted to do it separately, so let's say you didn't like the spicy way and you said, well, I just want to play it safe, do it separate. You'd get 1/2 times e to the u as u runs from -1 to 0, plus 1/2 times e to the v as v runs from -1 to 0, which is 1/2 e to the 0th minus 1/2 e to the -1st plus 1/2 e to the 0th minus 1/2 e to the -1st. Those two combine, everything like that. So you'd have 1/2 minus 1 over 2e plus 1/2 minus 1 over 2e. So whether or not you choose to do the spicy thing, make them into the same variable and work from there, doesn't matter. You get the same answer at the end, which is nice. Let's do one more example, and we'll call it good. The other example is, what happens if you have more than one curve, right? Let's say we had something like, find the area of the region bounded by f of x equal to x, g of x equal to 4 minus x squared, and h of x equal to negative 3x. Whoa, what does that even look like? Well, if you were to sketch it, you would see that the region would look something like, all right, here's where g of x would be, f of x is just a straight line, and h of x would look kind of like that. So what's the region bounded by all three? It's the one that's inside of all three of them. This thing right here. Do you ever have an argument for there being another closed region? Yeah, I guess you could try to argue it would be here or here. Okay, to prevent any argument that, what if you meant this area, or what if you meant this area? What we could do is say, we don't even have to phrase it this way, of the area bounded below by f of x equals x and h of x equals negative 3x and bounded above by g of x equals to x squared minus 4. All right, there we go. That's a better way to phrase it, so that way we know we're referring to specifically this area. It's above by x squared minus 4, below by negative 3x and positive x. Okay, so how the hell do we even go about setting up this integral? Here's what we're going to notice. Our theorem, where'd my red chalk go? Our theorem only allows us to compare two integrals at a time, right? It says if f of x is greater than or equal to g of x, here's that area. Here we have three functions. We can split it up into regions where only two functions are at play at the same time. How are we going to do that? Red line, right there. In this region, only g of x and h of x are at play. As soon as we cross 0, then only f of x and g of x are at play, right? H of x is all the way down there. We don't even care about what's going on over there. We just care about that part. And over here, we didn't care about f of x. We only cared about h of x and g of x. So if we split it up like that, now we have two regions that we can start working with. Okay, how do we do it? Well, we need to find all those intersection points, right? So if we solve h of x equals g of x and f of x equals g of x. Why? H of x equals g of x will give us those 2 points. F of x equal g of x will give us those 2 points. Alright, let's compute some intersection points. So, h of x equals g of x. Solve that, we're solving negative 3x equals 4 minus x squared. So x squared minus 3x minus 4 equals 0. That factors very nicely as x minus 4 times x plus 1 equals 0. So x equals 4 or negative 1. So that would say, oh, x could be down there, or it's negative 1. Oh, sorry, we need one more. We need h of x equals f of x. We need all three of the pairs. Sorry, h of x equals g of x will give us this, f of x equals g of x will give us this, h of x equals f of x will give us that. That's all we need. Alright, so x equals 4 or negative 1. Clearly, it's the negative 1 we're working for, since we're working with something to the left of the y-axis. Alright? How about, let's see here, f of x equals g of x. Well, we're solving x is equal to 4 minus x squared. So x squared plus x minus 4 equals 0. This also factors very nicely as x minus 1 times x plus, sorry, that does not factor quite as nicely as that. Give me half a second. Never mind, that doesn't factor as nicely as I thought it did when I set this whole problem up. But that's okay. We'll use the quadratic formula and that'll tell us the roots. So this says here, x will be negative 1 plus or minus the square root of negative 1 squared minus 4 times 1 times negative 4. Yeah, that's why the square root doesn't pop out quite right. Don't want to erase this. Carrying on from over there, this is equal to negative 1 plus or minus the square root of 17 divided by 2. Alright, so we're going to choose the positive option, since if we choose the negative one, we'd have a negative number, but we're working with the intersection of f of x and g of x, which is a positive thing, so we choose the positive. Let's label both of these on our graph, and then we can go from there. Here is negative 1. Here is negative 1 plus the square root of 17 divided by 2. So, again, this is why the picture is so important, because how would you know to choose negative 1 instead of 4, and how would you know to choose the positive 1 here? Only by looking at the picture and saying, this is below the y-axis, so I need negative 1. This is over to the right of the y-axis, so I need a positive number. If I chose negative, it wouldn't be a positive number, so I need the plus sign. Alright? So we have those two. We need to find the final one. It should be at 0. And we'll see that real fast. If we do h of x equal to f of x, we solve negative 3x equals x. Cool. Adding 3x on both sides, 0 equals 4x. So 0 is x. So this is, in fact, 0 as claimed. And please note, we don't need the y-coordinates for any of these. The x-coordinate alone suffices. Alright, now we're going to go. Also, quick thing, I just noticed, so I paused the video to confirm. I had g of x was equal to x squared minus 4. This should have been 4 minus x squared the entire time. And as for that impacting our finding of negative 1 right there, we'd still have x squared minus 3x minus 4 equals 0. So that still gives us x minus 4 times x plus 4 equals 0. I did this right even if I had g of x written incorrectly. So We're safe. It all works out. But yeah, that should have just been 4 minus x squared all along. This also still holds properly. All right, so where do we go from here? Now we set up our integrals. Our final area, the thing we want, is the area on the left side of this red line plus this area on the right side of the red line. How do we find it? Well, we're going to say integrate from -1 to 0 of what minus what? G of x is greater than or equal to h of x. On -1 to 0. So that's what we're going to integrate, is g of x minus h of x. Plus the integral from 0 to -1 plus the square root of 17 divided by 2, which, just so I don't have to write that out every time, I'm going to give it a handy little name. I'm going to call it alpha for now, and then we'll put it back in later. G of x is above f of x from 0 to alpha. And we see that here. It's bound below by these things and above by this, so the g of x should be the bigger one. So we're going to have the integral from 0 to alpha of 4 minus x squared minus x dx. Alright, and again, alpha is just our fancy name for this quantity because I don't feel like writing it out every time. It's a lot to write. I'm kind of miffed because I thought when I wrote this example, I was like, oh yeah, the roots will be nice. But that's not nice. Live and learn. Okay. So if you do this integration, you get the integral from -1 to 0 of -x squared plus 3x plus 4 dx plus the integral from 0 to alpha of -x squared minus x plus 4 dx. Put that all together, you get -x cubed over 3 from -1 to 0 plus 3x going from -1 to 0 plus 3x squared over 2 going from -1 to 0 plus 4x going from -1 to 0 plus, well, minus x cubed over 3 going from 0 to alpha plus, goodness gracious, falling apart in this last example here, minus x squared over 2 going from 0 to alpha plus 4x going from 0 to alpha. Alright, and then let's evaluate that a little further. That's equal to, that's that. Plugging some things in and checking all the things that will cancel away from each other. You'll have what? Negative, so positive, -1 cubed, which is -1/3. Right? Yes. Plus, okay, so that'll be minus 3/2. So you'll have -1/3 minus 3/2. Let's see here. That'll be -4. Yeah. So plus 4 right there. All right, let's see here. All right, so we have the plus 4 here. Then from here, just plugging in alpha, you're going to have minus alpha cubed over 3 minus alpha squared over 2 plus 4 times alpha, which is equal to what? Well, okay. If you plugged alpha into a calculator, you'd get roughly 5.924. You plugged all of that into a calculator. Again, I'm sorry that the alpha didn't turn out quite as nicely as I would have wanted it to, but live and learn. The main takeaway for this is, hey, if you have a setup that looks like this, you can divide it into 2 and work with each region separately, finding all your intersection points and then doing the analysis from there. It doesn't matter necessarily that we have an ugly number at the end. All right, I think that's all for now. Lesson learned. I should have probably made this like 2x or something like that. I don't know. Have a great rest of your guys' day.